Okay, so today we're gonna discuss something about the dispersion strengthening and the eutectic phase. Okay, so what's the objectives in this chapter? What we should learn from dispersion strengthening and the eutectic phase diagram. So what we get to learn is the dispersion strengthening effects. Okay, and what's this effect on the mechanical properties of metallic materials? Okay, and how can we find out the melting temperature and the phase transformation and the composition at the eutectic phase diagram? So if I provide you a phase diagram, can you tell me which point or which reaction or which composition is the eutectic reaction? Eutectic reaction. Okay, and we also have to know the amounts and the composition for each phases for any point on the eutectic phase diagram. Okay, and what's the alloy's composition based on its cooling curve? Okay, cooling curve. Okay, so in dispersion strength alloys, small, strong, and hard particles of one phase, or it can be regarded as precipitates, are introduced into weaker but ductile second phase or matrix. Okay, that means you have two phases alloys. One phases, the first phase is quite ductile, and the other phase is brittle. Okay, or brittle. Okay, and the dispersion strength in alloys might be produced by a eutectic reaction. It's quite important, such as cast iron or aluminum alloys, in which a liquid solidifies into two phases. Okay, I'll introduce this reaction later. This reaction is the transformation from the liquid into two solid phases. Okay, and this reaction is called the eutectic reaction. Okay. Okay, so why the eutectic reaction is so important? So let's look at the following. If the goal is increased strength and toughness, the following guidelines should be followed. First, the matrix should be ductile, right? As I already mentioned before, the matrix, the second phase have to be ductile, and the dispersion phase have to be hard and strong. That means brittle, such as brittle, okay, kind of brittle. And disperse phase should be discontinuous, okay, discontinuous. Why the matrix should be continuous, okay, and dispersed phase particles should be small and numerous to better prevent slip. Okay, therefore the dispersed particles are hard and strong and small and numerous that can prevent the slip process. Okay, that's mean you can stop the it can be as a barrier for dislocation. Okay, and those dispersed particle should be rounded, less likely to initiate crack propagation. If this dispersed particle is not rounded, it's not wrong, or it's a different shape like spike or tendril, and those shape will initiate crack propagation. Okay, will initiate the propagation, and usually higher concentration higher concentration of the dispersed phase increase the mechanical strength. Okay, increase the mechanical strength. Okay, so let's look at this picture. And those pictures tell us and which one's good or poor for this dispersion strengthening. For example, for the figure A, left is it's a good dispersion. Why? Because this dispersed phase is hard and strong, and the matrix is soft and ductile. Okay, if this alloy withstand stress or withstand different stresses, the crack will be initiated inside the dispersed phase first. Therefore, the crack will be here, initiated here, or propagated here. Okay, propagated here. Okay, and you may ask whether this crack will propagate through the ductile matrix. It is quite not possible that the crack propagates can be through the ductile materials. Okay, and because those precipitates are brittle, right? Are brittle, or it will be crack initiate first, and the matrix materials is quite ductile. Therefore, the propagation, the crack propagation, is not easily to trigger in the ductile material. Okay, it's not easy to trigger. And let's look at the figure on the right side of the figure 8. It is a poor dispersion strengthening. Why? Why? Because the matrix is hard. That means it's brittle. Right? The matrix is brittle. And the precipitate or the dispersed phase is soft. That means the crack will propagate through the matrix, right? Because the matrix is brittle. And the precipitate, the second phase, the dispersed phase, is soft. Okay, and also we need a smaller precipitate particles, like the figure B on the left. Okay, and usually smaller is better. Okay, smaller precipitate or smaller dispersed phase is better than the bigger size. Why? Can you tell me the mechanism of this the inferences of the particle size? The particle size of the precipitate phase. Did you expand it? If this phase and this phase is hard, and this phase and this phase is ductile. Okay, so why the smaller dispersed phase can provide a higher mechanical stress than that of the larger size of the dispersed phase? What's the mechanism? Can you explain that? Can you explain the effect of the dispersed phase size? Okay, so for the smaller dispersed phase or dispersed particles, that it has the higher possibility to stop, to retard the dislocations. Okay, if there's a dislocation happen here, and here, and here, and here. And when you move, you will move here. Oh, stop it, right? Okay. When you moved here, okay, it be stop. Here, stop. Here, be stop it. Okay. Okay. If the particle size, the dispersed phase size is larger, so what's going to happen from the dislocation movement point of view? For example, I have dislocation here, right? Edge dislocation. Well, there's nothing to stop me. I will keep moving. Okay, I'll keep moving. Right, no problem. Okay, if I have a dislocation here, well, there's no any barrier in front of me, so I can keep moving. Right? You know what I'm saying? Of course, if I have a dislocation here, it will be stopped here. That means for the larger size of the dispersed phase is not easy, or it's not able to stop this dislocation movement. Okay, and also for the failure point of view, that the crack will be initiated in the larger dispersed phase. Okay, for example, if we have a larger size of the dispersed phase, and the crack will be initiated inside here, inside this dispersed particle, right? Will be here. Okay, the crack will propagate through this larger dispersed particles. Okay. Okay, for the smaller one, the crack is not easy to initiate. Okay, because the stress applied will be distributed. Okay, will be distributed on each particle size. Okay, and the matrix. Okay, and also the shape of the dispersed particle. Round is always better than other shapes. However, round shape, right? Okay, so this round shape is much better than that of the like this needle shape. Why? Because if this alloy is withstanding some applied stress, and its dispersed base is needle-like. Okay, and this alloy is easy to trigger the dislocation, or easy to trigger slip, or easy to trigger the crack. Okay, because we have the sharp tip right here, right? Sharp tip, different shape right here, right? Maybe my applied stress is like this direction and this direction. Okay, so you must remember the fracture mechanics that we already taught in previous slide, previous chapter, right? So this is the tip. Okay, the crack tip, my foam here, and the stress concentration be here. Okay, and the figure D shows the density of the dispersed phase. Of course, the higher density as the can provide the higher mechanical strength than that of this lower density of the dispersed phase. Okay. Okay, so let's introduce the other compound. Is called intermetallic. Okay, intermetallics, which contain two or more metals in a single phase. They are often hard, brittle, so they are commonly used as dispersed phase. And stoichiometric intermetallic compounds has a fixed composition and are overused to strengthen steels. Non-stoichiometric intermetallic compounds has the range of composites, and intermetallic compounds has the structure, aerospace, and macroelectronic applications. Okay, so let me introduce what is the stoichiometric intermetallic and the non-stoichiometric intermetallic. Okay. Okay, so let's look at this binary phase diagram, right? Binary, that's mean two components. Okay, and on the left side is aluminum and what? Antimony, right? Antimony. And the binary phase diagram on the right is molybdenum and what? Rhodium, right? Rhodium. Okay, so both are binary phase diagram. Binary phase diagram. Okay, binary phase diagram. And so, and how to tell the stoichiometric intermetallic compound? First, we need two or more components, right? Therefore, we can find out this component from the aluminum antimony phase diagram here. It's a gamma phase. I call it's got gamma phase, composed of two elements, aluminum and antimony, right? And it has a fixed composition only at here. It's about 82%. It's right here. Yes, it can only occur at 82% of antimony. Okay, antimony. Therefore, its composition is fixed. It's fixed. You have to remember that. It's called a stoichiometric intermetallic compound. Gamma phase. For the molybdenum and the rhodium binary phase diagram, which has the non-stoichiometric intermetallic compound. It provides a range. Okay, it is a range. Okay, let's see, it's a range. Okay, it's a range. Okay, from about 40 to maybe 82% of rhodium. Okay, in this region. Okay, so which one provide the which intermetallic compound has the higher mechanical strength? They are the intermetallic compound gamma. Of course, the stoichiometric intermetallic compound provide a higher mechanical strength than that of the non-stoichiometric intermetallic compound. Okay. So there's some the table shows the some properties of the intermetallic compound. Okay. So you can compare its structure and melting temperature and Young's modulus. Okay, usually the intermetallic compound has the higher melting temperature, indicating that its strength is higher than others. Okay, so you can see the molybdenum and silicon, right? So its melting temperature is about 2000. Okay, and its Young's modulus is about 430 gigapascal. Okay, so the intermetallic compound, or just say it's a IMC, is neither a pure metal element nor alloy. So IMC is a chemical compound that chemically combined by two or more elements. Okay, so do you think it is a good compound, or is a good composite, or compound metal compound? We already know that for the dispersed phase, whose property should be hard and strong, right? The small, of course, as the dispersed phase for strengthening. So IMC, intermetallic compound, is the one of the best choice, right? However, do you think it is always good for mechanical strengthening? Of course not. Let me show you an example. So this is for the package, electronic packaging. This is a solder. Okay, so we have a solder. For example, we have a chip on top right here. Okay, we have a chip on top, and this is a flip chip bonding, flip chip bonded electronic devices, and we have a solder is bonded to a copper pad. Okay, it's the copper pad. You have a solder. Okay, so you can imagine that when you are playing the video game. Okay, when you are watching a movie or whatever, use your cell phone or laptop or desktop. So the thermal cycling is one reason to cause this chips failure, right? This chips failure. Okay, so and why the chips always fail from the thermal cycling? Because the thermal cycle might trigger the intermetallic compound form between the solder and the copper pad, like this figure. Okay, so its driving force is diffusion, right? It's diffusion. Okay, it's diffusion. So it's tin, right? Solder. The major component of tin of solder is tin. Okay, and the bottom, the connecting pad is copper, right? It's copper. So they must have the reaction, have a diffusion reaction in between, right? During this thermal cycle. And gradually, this intermetallic compound between the solder and copper pad must form here. This is the intermetallic. Okay. Its hardness is close to ceramics. So what's going to happen if you have a ceramics as an interface between two metals? You will break easily, right? You will break easily because this is, you can imagine that the tin is quite ductile. Okay, copper is ductile also. However, the intermetallic compound is brittle, right? It's brittle. So if the cell phone or laptop withstand a certain impact force, impact loading, or any stress, what's going to happen? What's going to happen? You will be broken here, right? Right? It will be broken from the intermetallic compound phase, interface. Okay. Therefore, for the electronic packaging point of view, IMC is not the welcome compound. Okay. So let's look at some phase diagram, some three-phase reaction. So as I already mentioned that the eutectic reaction. So what's the definition of eutectic? So the reaction occurs the single phase liquid transform into two solid. What two solid? Alpha solid solution and beta solid solution. Okay. Okay, so from any phase diagram, we can find out this reaction from liquid converted to two solid phases, and it is the eutectic reaction. So from the phase diagram, you will see this. Okay, so for the binary resistance might produce complicated phase diagrams such as those involving three signal phase. Let's focus on the eutectic first. So you can see this temperature right here. This is the first temperature, right? This horizontal line here that involving three phases. So what's this three phases? One is the liquid phase, right? And the other is the alpha solid solution and beta solid solution. Okay, so which point is the eutectic reaction? Which point? Could you indicate? Could you point out? Could you point out from this figure? Okay, let's mention that this is the figure 1, 2, 3, 4, 5. Okay, so from the first figure, can you point out which point is or which composition is the eutectic reaction? So as I already mentioned that the eutectic reaction is that the liquid phase transferred into two solid phase, right? Liquid and solid, solid. So which point? Here, right? Here, this point, right? Therefore, we want to find out the eutectic reaction. Oh, from the phase diagram, we can look at this shape. The figure, in the first figure, when we find out this shape in the phase diagram, so we know, oh, that point is the eutectic reaction. That composition is the eutectic composition. Okay. Therefore, from this phase diagram, I can draw a straight line here, right? Therefore, I can know its composition and its temperature right here. Okay. Therefore, we can fix the composition here and heat it up at the melting temperature here and cooling down. Okay. Therefore, there's no any two-phase region existed. Okay. At this composition and cooling down, there's no two phases. It will transfer from the liquid to two solid phase immediately once the temperature lower than this temperature. Okay. Okay. So for example, I have this. Okay, is that clear? This point and this point. Okay, for example, I heat it up at this point and keep cooling down and keep cooling down. So there's no two-phase region, right? You are from the solid, from the liquid phase converted to two solid phase, alpha plus gamma. Alpha plus beta. Okay, and for the peritonic reaction, still involving three phases, alpha, liquid, and beta, right? So in this figure 2, we can find out the concentration at this point. It is the peritonic reaction, right? So its initial phase is alpha plus liquid. Okay, solid, liquid, solid. Okay, there's no two-phase region. Okay, and so on. Well, the same as following that the eutectoid reaction is from solid, right? Solid and solid. Okay, therefore it's eutectoid reaction is here. It's here. Okay, and the pretectoid reaction is from solid, solid, and solid, right? Two solid into one solid, and this one solid convert into two solid. Okay, so it's a two solid alpha plus beta, and convert it to one solid gamma phase. Okay, therefore, once you can find out those shape in the phase diagram, those shape from the figure 1 to figure 5, if you can find out those shapes in a phase diagram, so you can tell, well, it's a eutectic reaction, it's a protetic reaction. Okay, and why it is important? Why it is important? Okay, so for the eutectic or protetic and metatic and so on, whatever, this reaction are part of this solidification process. Okay, and the eutectic reaction occur in alloys used for soldering and casting. The monothetic reaction improves the machinability of the copper alloy. The protetic reactions leads to non-equilibrium solidification and segregation. Okay, therefore we know, oh, we don't want, maybe we don't want this protetic reaction because it let the non-equilibrium solidification and segregation, right? And if I want to make a casting tool, casting parts, or solder, well, I should use what? The eutectic reaction, right? Eutectic reaction. Okay, and here it mentioned that the eutectoid and the protectoid reactions are completely solid. Okay, right? So from the previous slide, we know solid, 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 right? Okay, and only it's important. Only the eutectic and eutectoid reactions can lead dispersion strengthening. Oh, so we find the answer that's why these eutectic and eutectoid reactions are so important from the phase diagram. Because if we want to, we need a disperse strengthening process occur, we have to find out the specific eutectic and eutectoid reaction at specific composition and temperature. Okay, if your temperature is not at the eutectic temperature or eutectoid temperature, well, the dispersion strengthening effect is poor. It's really poor. Okay, you know what I'm saying? Okay, so let's look at this example here. This is a binary phase diagram. This is a binary phase diagram. It's a copper and the what? Copper and silver system. Okay, so here is the 100% of silver and there's 100% of copper. Okay, so which point is the eutectic reaction? Sorry, yes, eutectic reaction. What is the eutectic reaction? Yeah, eutectic reaction is occurred from the liquid phase converting to two solid phase. Liquid, solid, and solid. Okay, so which composition, which fixed or specific composition in this phase diagram is the eutectic reaction? Here, right? Here. Okay. Okay. So this composition is about 72 weight percent of silver. And we can draw a straight line here. Okay. And this straight line is what? Eutectic reaction. Okay, it's eutectic reaction. Okay. And its temperature is eutectic reaction occurred at temperature 779 Celsius. Okay, therefore you can imagine we have a first case here. We heat up at a temperature at maybe 1100 and cooling down here and cooling down here. And when we're cooling down below the 800 or below the 778 Celsius here, and we're cooling here, we can find out there's no two-phase region in this reaction, eutectic reaction. Okay, therefore we can write it down. Write this reaction, eutectic reaction down. We have a liquid phase with 71.9 weight percent of silver. Okay, when we cooling, you will form alpha and the beta phase. And for the alpha solid solution, there's 8 weight percent of silver. For the beta, it has the 91.2 weight percent of silver. Okay, so this is the eutectic reaction. So you may ask, where's the 8 weight percent and 91.2%? Where is it? It's here. Here and here. Okay. Okay, regardless of solubility. Okay. So let's look at the other binary system or the eutectic phase diagram. It's a team-led phase diagram. So can you point out where's the eutectic reaction in this phase diagram? Or you can tell me the composition. Wow, it's about like 61.9 weight percent of tin, right? Therefore, we can draw a eutectic reaction here. Right, so here is the eutectic reaction. Right, there's no two-phase region here. Okay, so you were converted from the liquid phase into two solid phase. Okay, so try to write down its eutectic reaction. Or you can just try to write it down. Okay, and the lactin system contains only a simple eutectic reaction with four classes of alloy. And in this diagram, the alpha phase is a solid solution, and the lead with a small amount of tin as the solute. Okay, and the beta phase is a solid solution with solid solution of tin with lead as the solute. Okay, therefore for the alpha phase, tin is the precipitate is a dispersed phase. Okay, for the beta phase, that is the dispersed phase. Okay, it's a dispersed phase. Okay, is that clear? And this eutectic reaction occur at the 61.9 weight% of tin and the 183 Celsius. Okay, so when you just develop some solder, you want to disperse strength it, so you have to adjust the composition of tin at the specific point of 61.9 weight%. Okay, so when you just heat it up at maybe 300 Celsius and cooling down to reach the 183 Celsius, that the dispersed strengthening will be provided the precipitates. Okay. Okay, so let's look at this figure right here. This figure. So do you think it's I already mentioned that the phase diagram is made from the experiment, right? From the experiment, from the melting experiment of pure alloy and the pure metal and alloys, right? So do you think this figure is the eutectic point? I mean, this figure shows the eutectic reaction. I mean, I do the do you think so? And why? Could you explain it? Of course, yeah, it is, right? Of course, it is. Okay, so you might think of this question. Okay. Okay, so let's look at the eutectic phase diagram of a team-led binary phase diagram. So let me phase a composition right here. It's 10% of the right here. Okay, here. Okay, it's about 10 weight%. Oops. Sorry, it's about 10 weight% of what? Of tin, right? This point is about 10 weight% of tin, right? And I draw a straight line here, and I heat it up at maybe 350 here, okay, 350 Celsius, and I cooling down. So what's gonna happen? What's the phase gonna form during this cooling? During cooling. So you can look at when we from the point A to the point B, say here, point B. And what's the phase? What's the phase of the point B? It's a two-phase region, right? That means the solid and liquid coexisted, right? Here, this region. Oops, sorry. It's here, right? It's a two-phase region. So we're cooling down the temperature from 350 to maybe 300 something, and the solid phase begin to form, right? The alpha phase, okay, the alpha phase. So you will find out that this two phase region is between the two phase, right? Alpha plus liquid. So here is the liquid and this is alpha. Between them, this area is two phase region. Okay. Therefore, at point B, that means this alpha phase begin to form. And when we cooling down, keep cooling down the temperature to maybe say like here, point C is 250. So that means the liquid is completely converted, transformed to solid, alpha solid solution, right? Okay, like this case. And if we keep cooling the temperature to say the 100 Celsius here, the D, point D, if we will find out, wow, heat right now the beta phase form, right? Because in this region, it's the two solid phase, right? Alpha plus beta. Therefore, the beta phase form. Okay, beta phase form here. Okay, so can you draw or can you describe if I just indicate a specific composition? Can you describe its phase formation and phase transformation and what kind of phase will be existed? Okay, you know what I'm saying? And can you calculate its composition of each phases? Okay, that's the question we have to learn. That's the issues we have to learn from these chapters. Okay, so this I already described this early. So alloy containing a small than 2% of tin, a single phase, and are strengthened by strength hardening, controlling grain size, and solid solution strengthening. Okay, so what does this mean? Let's look at this figure. So with the 2%, it's right here, right? It's the 2%, this point here. Oops. Okay, this point is 2% of tin. This point. Okay, so I can draw a straight line here. Oops. Maybe from here. Whatever. I'm not a good draw this straight line. Okay, therefore it's pure tin, right? It's a single phase. Okay, when this content is smoother than less than 2% of tin, it's a single phase. Okay, it's right here. Okay, right here. It's a single phase. Only what? What kind of phase? Alpha solid solution, right? Alpha solid solution. Okay. If this composition of tin is smaller than 2%, it's a totally alpha solid solution. Therefore, the way the approach to strengthening is strength hardening, and we can control its grain size, grain structure, okay, and so on. And if the alloy existing its solubility limits, for example, the alloy with 2% of tin is this composition of tin is between 2% and 19%. Okay, that also produces a single phase solid solution. But after additional cooling, a second solid phase or solid solution phase precipitate out of from the first one. So what's that mean? Let's look at this phase diagram. So previously I already mentioned that if the tin composition is smaller than 2%, right? And now if this content of tin is between 2 and 19, right? So it's this range. I just draw on this figure. It's the two, right? Okay, it's two here, here to here to here to here, right? It's a 19, it's 2. And here, okay, within this range. Okay, alloys with this range also produce a single phase of solid solution, right? It's still a single solid solution, alpha solid solution. And if we could keep cooling down, still remember from this point to this point, right? To this point, okay? So if we keep cooling down, the second solid phase precipitates out of from the first one, okay? The beta phase, the beta solid solution, okay? Initially, you have the only have one solid solution phase. It's alpha, right? It's alpha. And if we keep cooling down to this point, that means the second solid solution phase form. Okay. Can you tell the difference? Okay. And the eutectic alloys, the eutectic composition is exactly 61.9% of tin. This composition has the lowest melting temperature, and the solidification occurs at the single temperature, not the range. A lamellar microstructure is seen. Okay, that's the reason why the eutectic alloy, the eutectic reaction is so important, because it has the lowest melting temperature. Okay, we don't need a high temperature, we just need a low melting temperature, and the uh, the uh, the strengthening, the dispersed strengthening is the optimum at this eutectic reaction. Okay, and the solidification occurs at a single temperature. What's the temperature? The lowest temperature, right? The lowest melting temperature. What's the temperature? Right, about 183 Celsius. 183 Celsius. Okay. And this temperature is melting temperature, right? If we look at this reaction, this eutectic reaction, okay. If we increase, if we heat this alloy, when this temperature higher than 183, you will transfer into liquid immediately. Therefore, this point is its melting temperature for eutectic reaction. Okay, for other composition, you can look at, if I just throw this line here, for example, oh, this may be 32 weight% of the tin, right? And what's its melting temperature? Right here, right? It's totally melt, will be around here. It's about 200 something, 250, right? You will convert it to the completely liquid. However, for the eutectic reaction, these solids, two solid phase converted to the completely 100% liquid, its temperature is about like 183. It's the lowest melting temperature. So you can think of, well, it's has the lowest melting temperature, and it can provide the a good dispersion strengthening. Okay, and it's a lamellar structure. Okay, it's a lamellar structure. Okay. Okay, so next I'm going to introduce what is the hypo and the hypereutectic alloy. Hypoeutectic reactions occur between the left end of the eutectic reaction timeline and the eutectic composition. Okay, and the hypoeutectic reactions, the liquid begins to solidify and the liquidus temperature, producing one solid phase. Okay. For the hypo, okay, the liquid began to solidify at liquidus temperature, produce one solid phase. Okay. So let's look at this figure. We already know that this line, this composition is the eutectic reaction, right? And mention that on this left end of the eutectic reaction timeline, the left end of this eutectic timeline was this. What's the point? It's this point, right? It's this point. Okay. On the left here. That clear? Okay. So if we draw, if I just say it's about the composition is about like 38% of tin right here, and we draw a straight line, and we cooling down from like 350 Celsius from here to here to here to here. Okay, A, B, C, and D. So what's going to happen in its microstructure when we cooling down from point A to point D? Okay. So this is the eutectic, right? And this left-hand side is hypo. Okay, hypo. Okay. So we can just find out initially it's liquid, right? And the temperature just decreased to like maybe 250 or 240 to reach the two-phase region here. This is the two-phase region, right? With alpha and liquid, alpha solid solution and liquefies. Okay, and when this temperature reach the it's called the eutectic temperature is 183. What's gonna happen? I already mentioned that this eutectic alloy is lamellar microstructure, right? When you observe this lamellar structure from your microscope, you know, wow, it's a eutectic alloy. So this lamellar structure begins to form here. This is the lamellar structure, layer structure. Okay, this is alpha solid solution. And this is the lamellar structure, layer by layer. And this lamellar structure keep growing, okay, during the temperature decrease. Okay. Okay. Therefore, when we just when this temperature keep cooling to point D, we'll find out this lamellar structure is completely grown. Okay, it's completely grown. Okay. Okay, so we can see that if the composition of tin, when this composition of tin is 61.9%, this is the shear stress. Okay, shear stress with the composition of tin. Okay, so what's the result is? That is, we have the higher shear stress at this eutectic point. Okay, at the eutectic point. Okay, if this composition on the left of this eutectic reaction is called hypoeutectic. If this reaction is on the right of this eutectic reaction is called hypereutectic. Okay, no matter it's hypo or hypereutectic, its mechanical property is poor than that of the eutectic reaction. Okay, therefore here is hyper. Okay, so you can try to plot this microstructure if I draw a composition line right here. So can you point out what's a microstructure here and here, 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 and here? Okay, I just tell you the result is that for the hyper-eutectic, it's a lamellar structure with alpha solid solution. Okay, for the hyper-eutectic, the microstructure is the lamellar structure with what? The beta solid solution. Okay, the beta solid solution. Okay, and this is the shear stress. Okay, and if we compare other mechanical property, this for the shear stress, I already mentioned that, and this is a tensile stress. Okay, it's a tensile stress. It has the same mechanical performance that we have a composition at 61.9% of tin. Its UTS is the highest one. Okay, it's the highest one. Okay, so on its left is hypo, and its right is hyper. Okay, for the hypoeutectic, the solid solution strengthening of alpha by tin. Okay, initially, and then the dispersion strengthening of alpha by beta. Okay, and keep increasing eutectic. Okay, therefore, that's why I mentioned that the eutectic composition is important for the dispersion strengthening. Okay, because it has the lowest melting temperature, it has the highest mechanical property. Okay. Okay, so maybe I'll stop the course here, and maybe we'll have the other course to describe the relation between the cooling rate and the eutectic reaction. Okay.